European Pharmacopoeia is a single reference work for the quality control of medicines. And also the official standards, it contains, provide the scientific basis for quality controls during the entire life cycle of a product. These standards are legally binding, as laid down in the Council of Europe Convention on the elaboration of European Pharmacopoeia in the EU and national pharmaceutical legislation. And they become mandatory on the same date in all states parties to the convention, let's say. Just some information about it. That's really important, actually. Defines somehow how we measure quality and what the quality of specific plants would be. Legally binding in 39 European countries and applied in more than 120 countries worldwide. This implies also that is a common approach, a common framework, I would say, when we deal with medicinal plants and quality, and delivers crucial information for European markets earlier than any other pharmacopoeia. Now, the 10th edition includes a supplement 10.7, contains 2,463 monographs, and 383 general texts, including general monographs, methods of analysis, and about 2,850 descriptions of reagents. The example that we used before, I have also copied, a paste here, how you see the different aspects that should be considered in terms of quality of Melissa leaf, for example, lemon bulb leaf here. We need to have dried leaf, and we should really keep this guideline somehow. We need to have an air-dried leaf with a maximum 10% of stems, maximum 2% of foreign matter. The moisture content should be not more than 10% in wet basis, and we should have also a minimum 1% of rosmarinic acid. Also, European Pharmacopoeia, also I said that gives us also indication of how we measure, let's say, quality parameters. And hydrodistillation is a method described by the European Pharmacopoeia for volatile extraction. And in almost all plant species of Lamiaceae, essential oil is synthesized in two basic types, as we see here, of glandular hair, such as peltate and capitate. And in the case of lemon balm, oil glands can be found on both sides of the leaf, but they are mainly distributed on the lower epidermis, while this is related with the other slide that I showed you before. Here we see only the oil glands, these small oil glands, but on the other side, you can see also the high density of single spiny hairs that exist on the upper epidermis of the leaf. And hydrodistillation, as said, is a method, as we see on the right-hand side, a simple method for volatile oil extraction. And the equipment used is called Clevenger apparatus. And extraction of, just briefly about the extraction of bioactive compounds or active ingredients in the essential oil. Hydrodistillation is coming from the word hydro, of course, uses water or steam as an extraction solvent to recover volatile or polar components of plant materials. And it's often carried out using a setup known as this apparatus that I told you before, the Clevenger, or simple steam distillation. And what we have assembled mixed water is boiled to evaporate volatile components, while in the steam distillation, the steam is passed through a bed of the sample. In both approaches, two layers, aqueous and oil-rich, are obtained, and oil can be further separated via separating funnels. In this technique, separation of aroma compounds from water, particularly polar ones, is a challenging, I would say, task, and perhaps the greatest limitation of hydrodistillation type extraction, of course. What I would like to show you, just to give you as I hope that I have done today in all my presentations, just to give you a more lab and practice-oriented approach besides reading, let's say, just some fundamentals or disciplines and so on. Therefore, many disciplines involved in this sector. Therefore, what we see here, we see experimental data points of essential oil content changes, and curves are the solid lines, of course, predicted by a model that we have developed during convective drying at different temperatures, ranges from 30 to 90 degrees. And it's important to note here that drying was terminated when a constant mass has been achieved, regarded as the equilibrium moisture content, what we have discussed before, for the respective drying condition, different for 30, 45, 60, 75, and 90 degrees. And we see here that the oil content, the essential oil content, was decreased gradually as the drying progressed. And in particular, most of the essential oil was observed at the beginning of the drying of all examined temperatures. Just to give you an example here, what we see in the graph, leaves subjected to 30 degrees Celsius resulted in less than 60% of oil reduction within the first during the first 6 to 7 hours. Indicating a remarkable stability as drying continued, as we get the dried product, let's say. A similar behavior was also noticed at 45 degrees Celsius, however, with greater essential oil losses in a shorter time, 21% after 3 hours of drying. And of course, this phenomenon is obvious here. It was more severe with progressive increase of drying temperature of up to 75 degrees Celsius. More specifically, drying for 30 degrees for 30 minutes at 60 and 75 caused considerable loss of 45% and 70% in oil content respectively, is what you can see in the second, in the right-hand side graph, when we quantify the essential oil losses in percent per drying temperature. The sensitivity of leaves, of lemon bulb leaves to higher temperatures can be ascribed, of course, to volatile component constituents found in essential oils. Also, higher drying temperatures, as you see in the scanning electron micrographs here, might have ruptured the oil glands, these sensitive glands that we saw before, causing rapid evaporation, of course, vaporization of essential oil. It is worth mentioning here that in these bars here, in this graph that we quantify the loss of essential oil, we have kept the final moisture, the target final moisture content was same for all samples, was 11%. What we said before, this information that we got from the desorption isotope. And you see how all different parts, drying, essential oils, quality, moisture absorption are interlinked somehow. And it's obvious that above 45, of course, 45 also is a trade-off between quality and drying, but above 45 is not really recommended to dry lemon bulb. I would say 30 degrees, but 30 degrees has another issue with the prolongation of drying time. Therefore, it's always a trade-off, between drying cost, drying time, and quality to be achieved. If we have a closer look now to the essential oil constituents, what we observe here is that we have pronounced changes in the major essential oil components at 60 degrees, like neral, geraniol, citronellal, where their content decreased, while citronellol indicated an increasing tendency. Therefore, again, depends, the condition on the end user. If, for example, we need citronellol as a final component, optimum was achieved at 60 degrees Celsius. It was quite contradicting and strange result, I would say, but this is research. Another important parameter to measure is color, and how we do that. There are simple sensors already established. They have been defined by CIELAB in 1976 for color communication. I would say this approach is commonly adopted today in many industries for color control and management, also in this industry of medicinal aromatic plants. And what we have an LAB color space. L indicates lightness, A and B are chromaticity coordinates, and A and B are color directions, as we see here in the graph. We have, let's say, A plus is the red axis, A minus is the green axis. And B plus is the yellow axis, and the B minus the blue axis. And area around the center represents, of course, achromatic colors, and moving outwards, color saturation, of course, increases as another parameter. And this can be measured by chromometers developed by company Minolta, very popular, that is handheld, portable measurement instruments, and is used really frequently to evaluate color, with the support of a software, SpectraMagic, as we see here, that is compatible with an optional data processor, and you can also print on-site results based on your measurements. Some results that we have obtained and validated actually in drying practice. The course of color changes of lemon bulb again was examined during hot drying at different temperatures again, ranging from 30 to 90 degrees Celsius. We had kept constant specific humidity of drying air to 10 grams per kilogram and an airflow rate of 0.2 meters per second. We said all these experiments should be carried out at really predefined conditions. And then you see lines again, you see data, you see standard deviations, okay? We tried also to develop a generic model to predict such changes based on the data we have measured, acquired. And the data were fitted to a first-order reaction kinetic model, and we try also to integrate, to embody to the model the temperature dependence of the rate constant using a simple Arrhenius type, as you see here, relationship. What we observe here is that the A on the top, redness, and B, yellowness of the leaves, values were the most sensitive parameters to describe the color changes of lemon bulb during drying. Redness, degree of redness, the product becomes more red, let's say, increased, while yellowness gradually decreased as drying progressed towards equilibrium moisture content. And again, a very important point for stepwise strategies, for stepwise drying strategies in the future is that the color degradation immediately started in the beginning of the process, when moisture content was still high in the material. And you see now how moisture content plays a role in these quality changes during drying. Most of the changes occurred in the beginning of the process and not towards the end when the dried material has been obtained. Here an approach also to bring all parameters in one graph, also to give you a visual representation of the plant material dried. It's obvious that 30 degrees Celsius was the best condition to dry lemon bulb. Then at 45 degrees, we developed somehow an olive, dried leaves with an olive, I would say, different than the fresh ones, or they have an olive hue in terms of chromaticity, but I would say 30 degrees was the best one, followed by 45. Again, it's trade-off. If color is not a primary quality criterion, probably we can go for 45 because we have reduced the drying time tremendously. But of course, 60 or 75, 90 is not recommended for green leaves of lemon bulb. It's obvious here that the material was totally brown, dark color. And this also implies, changes in some quality characteristics, as we see here. The color probably can be used as an indicator of other component changes during drying, losses, for example. And what we noticed that leaves dried at 30 degrees Celsius were rich in hydrocycinamic acid derivatives. In other words, rosmarinic acid equivalents were really high at 30 degrees, reduced slightly by 45 and tremendously by 60 and 75 degrees Celsius. Therefore, color, as said, can be used, and especially here we see I have highlighted in red hue, can be used as an indicator for quality evaluation. We can develop sensors, let's say, based on color measurements, and then correlate these measurements with rosmarinic acid and try to explain of course, the physical significance behind the physical and biochemical significance behind. But here what we found out is that color can be used as an indicator of rosmarinic acid in lemon bulb. This can be probably extended to other plants, similar plants like peppermint or basil. And what we have found is by measuring color, we we can't really know the content of rosmarinic acid in our plants. That is really difficult and complicated to measure. I mean, you need a special lab, special procedures to follow protocols and so on. Therefore, a color change can give you an indication of the rosmarinic acid content in the plant. That is also a quality criterion that prescribed in European pharmacopoeia. I would like to go briefly just to give you an overview about other drying technologies that can be used in our sector, in the medicinal plant sector. Probably you are aware about vacuum drying or freeze drying. Vacuum drying has some distinctive characteristics such as higher drying rate, lower drying temperature, and oxygen-free process environment. We know that our plant material, when harvested, are really sensitive, I would say sensible to oxidation reactions. Therefore, with vacuum drying, we can offer other possibilities in terms of product quality in this field. And these, of course, features that I mentioned before are beneficial and help to improve the quality of dried herbs. And vacuum drying is conceptually a very good method, I would say, for drying thermal and oxygen-sensitive materials due to the advantage of removing water moisture, let's say, at low temperature and minimize the possibility of oxidation reactions. Just to give you a practical insight, vacuum drying, for example, when we dry herbs with a temperature of 25 degrees Celsius, can reduce or dries faster, 3 times faster compared to drying with warm or conventional air drying of 30 degrees Celsius and humidity of 50%. The method requires, of course, some type of heating in order to prevent or to maintain temperature drop of the drying material, and combine, of course, evaporation of water of moisture. And the heating the herbs with conduction heat from a heating plate in the container is also required to induce these evaporation processes. Also, another method, more complicated one, but very popular in pharmaceutical industry, I would say, vacuum freeze drying is mainly used to dry the extracts. I would say is not post-harvest processing step, is post-dry herb post-processing step somehow. Therefore, vacuum freeze drying is a method in which water vapor is mainly removed by sublimation from a frozen material, pre-frozen material, and by desorption in the final phase of drying. Is a process in which a completely frozen sample is placed under vacuum in order to remove water from the sample and allowing the ice to change directly from solid to a vapor without passing through a liquid phase. And as said, this is common as sublimation, and minimal heat input, of course, is required to induce this phase transition. And of course, is an ideal method for the long-term, due to long-term preservation properties, and provides high integrity of the sample's biological and chemical structure. I would say is a very good method to use, but also investment costs are some negative aspects here. Just some examples. We have carried out some examples, freeze dry using freeze drying, vacuum drying, and convective drying. What we have found out here is that in terms of essential oil, the geraniol content was higher after freeze drying or convective drying, while vacuum drying led to lower contents of nerol and geraniol. If you see now the bars here, when we try to quantify essential oil, total essential oil content losses, we see that the essential oil content of all dried samples was comparably lower than that of the fresh material. We had losses, particularly for freeze drying and convective drying. Total essential oil losses were about 15%, while vacuum drying caused more, 26% losses in essential oil. Also, using the scanning electron microscope, convective drying caused some shrinkage. You see here the material shrinks, whereas the structure of the cuticle of the vacuum dried sample was less affected, probably because of the low chamber pressure during the process. Also, a slight expansion of the leaf structure can be noticed. This might have caused volatile compounds to be released into the air. Very observable, noticeable, I would say, structural changes were developed by freeze drying. The freeze-dried leaves appeared wrinkled with minimal shrinkage but fragile structure. And this can be ascribed to the freezing temperature applied as well as to the pressure selected for sublimation of the pre-frozen material. You see here shrinkage in the convective dried samples, air-dried ones, and cell expansion in the vacuum-dried ones. In terms of color and rosmarinic acid, all methods develop good color quality, actually. Freeze and vacuum-dried sample exhibited also greater rosmarinic acid content that hotter dried leaves, but all methods, I mean, I would say rosmarinic acid from extract from all methods was acceptable. As you see, was above the limit, the threshold value prescribed in the European Pharmacopoeia. This study, however, indicated that aside from drying temperature, a decrease in phenolic compounds, even though a low temperature of 30 degrees, we said that rosmarinic acid is very heat sensitive, even a low temperature of 30 degrees has been maintained. Loss in rosmarinic acid can be also caused by the resulting long drying treatment, I would say. We evaluate also the sorption behavior, the effect of drying method on the sorption behavior, and here we see the different sorption characteristics were ascribed, of course, to modification in the matrix structure caused by the mode of drying, or better by the method of drying method. Sublimation of water vapor during freeze drying result in a higher sorption capacity, as you can see here in this figure, in this graph on the left-hand side. And the sorption isosteric heat increased as moisture content and temperature decreased, and increasingly sharply for equilibrium moisture contents below 0.2, as you will see here. And worth mentioning here to say that the freeze-dried leaves at equilibrium moisture content, that is what we need to know, was significantly higher than that of vacuum or dried materials. Also, scanning electron microscopic images present here. We try to get a picture, to get an image, let's say, of the cross-section we have of the leaf subjected to these three different drying methods. It's obvious that the tissue structure in the interior of the leaf was extremely affected after hotter drying. A similar observation was documented for the conventionally dried leaves by other plants, I would say. In contrast, the cells of the mesophilic layers inside the vacuum-dried leaves appeared less collapsed. In the middle, you can see that. On the other hand, less dense cell structure with signs of open pores developed between the lower and upper epidermal layers for the freeze-dried samples. Influence of drying method on microbial count of raw drugs. Here, what we see, this is actually microbial count of raw drugs, of raw plant materials, is a very important topic, I would say, because this represents a major problem for medicinal plant growers. Official threshold of colony forming units in terms of aerobic bacteria, molds, enterobacteria, E. coli are postulated in the European Pharmacopoeia. You can see here the different categories. Category, for example, A, there is a special category 4 for herbal medicinal products consisting solely of one or more herbal drugs. Category 4 is divided into 4A when boiling water is added before use, and 4B when boiling water is not added. Threshold of microbial count are higher for category 4A than 4B. Also relevant for medicinal plant production is category 3B, which is valid for preparation for oral administration containing raw materials of natural origin. Here, the threshold for microbial count are lower than in category 4, but in terms of aerobic bacteria are still higher than in category 3A, which is the most stringent one. And what we see here, we see that we have experiments with, in practice, post-harvest processes such as collection of plant material in the field, transport to the farm, and drying are often, let's say, suspected to increase the microbial contamination of medicinal plants. That was our hypothesis. And when the bulk of harvest material is not well ventilated, auto-heating due to respiration activity provides favorable conditions for microorganism growth in terms of temperature and humidity. And we see here a study on Hypericum perforatum, which revealed that the microbial count is already high before harvest. This is very important. It's already high in the field. And on the left-hand chart here, you can see that the most samples taken before harvest, and they just met the requirements of class 4B, I would say. Yeah? And drying the material in a conveyor dryer that we saw before reduced the original microbial count, and the raw drug met the highest quality classes of 3A and 3B. In a flatbed dryer, in the contrary, the microbial count could only be reduced in the bottom layer, meeting class 4A requirements. If we go into more detail about the microbial growth during drying, in the conveyor dryer, the microbial count of bacteria, molds, and yeast decreased continuously during drying, while in the top layer of the flatbed dryer, the microbial count increased. Why? We have in the flatbed dryer, you remember, we have a high bulk, high moisture is developed, and in the bottom layer of the flatbed dryer, the microbial count did not change during drying. Due to the high variability of the colony, the CFU, the colony forming units, differences were only significant for the decrease of bacteria in the conveyor dryer. You see the benefits by drying in thin layers compared to the really easy approach with a flatbed dryer and the bulky material. However, it can be stated that microbial count is already high in the field and is not increased during drying. This is also very important when state-of-the-art technology, of course, is used. Here I present there is already research done on that. They had investigating the effect of drying on active ingredients of medicinal plants. We have seen losses of active ingredients during drying for many different medicinal plants at different temperatures. But what we really need here is that we need experiments with a range of drying air temperatures to be performed for further medicinal, aromatic, and spice plant species, I would say. And as common reference for calculated losses of active ingredients should be the content in the fresh material. We should always keep to develop methods to analyze. It's much easier to analyze the dried samples, but we should always have a reference, the fresh material, or if not possible to, let's say, to quantify or to extract bioactive compounds by fresh material, just to define a standard methodology, let's say drying at 20 degrees Celsius, but in a controlled environment, not just placing a material in a room and just let it dry for many days. In a climatic chamber, if fresh product is not possible to be measured, let's say, because we have high moisture contents, and this actually affects the measurement protocol, if it's hydrodistillation, if it's HPLC or GCMS or whatever. We need to define a method, let's say 20 degrees Celsius. We can remove all humidity from the environment, and we can set this 20 degrees Celsius at low relative humidity levels as a standard, let's say, and then compare this 20 degrees with the rest of the conditions, 30, 45, 60, 70 degrees Celsius or so. Therefore, as said, we need a common reference for calculated loss of active ingredients. And of course, oven drying has to be prevented. This is a major issue by many researchers and by many people in practice. They over dry their products just to be sure that they will have they will prolong their shelf life. But this is a major mistake. We need to avoid over drying, and we need to dry to the optimum final moisture content. I hope that this message from my presentations today was quite clear. And of course, we have a very nice question from Argyro before. The drying experiments should be accompanied by analysis of active ingredients during storage. This is very important. Okay, we have got our dried herb, dried material. We should see that the compounds are in this dried herbal material are still active in a period of several months. Storage experiments for using the dried herbal drugs is very important as well. And besides the thin layer models that I mentioned before, we should extend to bulk models to estimate drying process that are more relevant in drying practice. Yeah, this can be done by, of course, modeling and simulations approaches by engineers. This is not a problem, but we need experimental data. This is the main issue. We need experimental data rather from the lab, can be from either from the lab or from the drying practice using industrial dryers. What we see here, we have a system, and I will close the presentation with this slide. I would say, I hope that I will not have more. And here we see an image, we see an online measurement system for moisture and essential oil contents. It has been used for parsley, and we use a near-infrared spectroscopy during conveyor belt drying. And as said, since major quality changes occurred in the beginning of drying, multi-phase drying process like stepwise increase of air temperature during drying should be investigated in future research. In addition to air temperature, we need also to measure the actual temperature of the material. Should be measured with sensors. It can be done now easily. Also can be measured non-destructively. We can use infrared thermography, therefore integration of multi-sensor approach, linking with my lecture yesterday would help, of course. Infrared thermography, for example, would help monitoring product temperature fluctuation during drying. And optical sensors, as I mentioned before, with rosmarinic acid, optical sensors based on color detection can be used for the non-destructive and online nowadays assessment of specific active ingredients, bioactive compounds such as rosmarinic acid. And of course, this method should be further, let's say, developed at commercial scale for inline monitoring of rosmarinic acid and validated using other plants as well, not limited to lemon balm, but also extended to peppermint, to basil, and all Lamiaceae plants that are all plants belonging to Lamiaceae family that are rich in rosmarinic acid. The rosmarinic acid is considered as major quality criterion, I would say. Again, just highlighting here the research needs from practice relevant to linked, connected somehow to quality. And I recommend also some papers for further reading. That's it from my side today. I hope you enjoy my long lectures today. Feel free to ask any question. You can contact me anytime, not only now during my presentation, but also after. You have my mail address here. Feel free to contact me and happy to discuss any point now. Thank you.